So let's continue with reading structure and interpretation of computer programs. And last time we left at symbolic data section 2.3. So let's start from here. All the compound data objects we have used so far were constructed ultimately from numbers. In this section, we extend the representational capability of our language by introducing the ability to work with arbitrary symbols as data. Quotation. We can form compound data using symbols. We can have lists such as sorry, this one. Lists containing symbols can look just like the expressions of our language. In order to manipulate symbols, we need a new element in our language, the ability to quote a data object. Suppose we want to construct the list AB. We can't accomplish this with list AB because this expression constructs a list of the values of A and B rather than the symbols themselves. This issue is well known in the context of natural languages, where words and sentences may be regarded either as semantic entities or as character strings, syntactic entities. The common practice in natural languages is to use quotation marks to indicate that a word or a sentence is to be treated literally as a string of characters. For instance, the first letter of John is clearly J. If we tell somebody, say your name aloud, we expect to hear that person's name. However, if we tell somebody, say your name aloud, we expect to hear the words your name. Note that we are forced to nest quotation marks to describe what somebody else might say. We can follow this same practice to identify lists and symbols that are to be treated as data objects rather than as expressions to be evaluated. However, our format for quoting differs from that of natural languages in that we place a quotation mark, traditionally the single quote symbol, only at the beginning of the object to be quoted. We can get away with this in scheme syntax because we rely on blanks and parentheses to delimit objects. Thus, the meaning of the single quote character is to quote the next object. Now we can distinguish between symbols and their values. Quotation also allows us to type in compound objects using the conventional printed representation for lists. Sorry. Car. Okay. In keeping with this, oh my god, this syntax is horrible, horrible. In keeping with this, we can obtain the empty list by evaluating and thus dispense with the variable nil. One additional primitive used in manipulating symbols is ek, which takes two symbols as arguments and tests whether they are the same. Using ek, we can implement a useful procedure called memq. This takes two arguments, a symbol and a list. If the symbol is not contained in the list, that is not eq to any item in the list, then memQ returns false. This is like the in operator in Python. Otherwise, it returns the sublist of the list beginning with the first occurrence of the symbol. Okay, false, otherwise the sublist of the list beginning with the first occurrence of the symbol. Okay. For example, the value memQ apple in this list is false, whereas the value of this is apple pear. Okay, I expect a bunch of exercises to make some practice with this syntax. Maybe I will do a couple of them, or maybe I'll do directly something more complicated. Example, symbolic differentiation. As an illustration of symbol manipulation and a further illustration of data abstraction, consider the design of a procedure that performs symbolic differentiation of algebraic expressions. We would like the procedure to take as arguments an algebraic expression and a variable, and to return the derivative of the expression with respect to the variable. For example, if the arguments to the procedure are the expression and x, the variable, the procedure should return to a x plus b. Okay, just computing the derivative. Symbolic differentiation is of special historical significance in Lisp. It was one of the motivating examples behind the development of a computer language for symbol manipulation. Furthermore, it marked the beginning of the line of research that led to the development of powerful systems for symbolic mathematical work, which are currently being used by a growing number of applied mathematicians and physicists. In developing the symbolic differentiation program, we will follow the same strategy of data abstraction that we follow in developing the rational number system of section 2.1.1. That is, we will first define a differentiation algorithm that operates on abstract objects such as sums, products, and variables without worrying about how these are to be represented. Only afterward we will address the representation problem. In order to keep things simple, we will consider a very simple symbolic differentiation program that handles expressions that are built up using only the operations of addition and multiplication with two arguments. Differentiation of any such expression can be carried out by applying the following reduction rules. Okay, these are the differentiation rules. Observe that the latter two rules are recursive in nature. That is, to obtain the derivative of a sum, we first find the derivatives of the terms and add them. Each of the terms may in turn be an expression that needs to be decomposed. Decomposing into smaller and smaller pieces will eventually produce pieces that are either constants or variables, whose derivatives will be either 0 or 1. So okay, these the first two rules are the base cases, and instead the third and the fourth rules, the third and the fourth rule are the conditions in which we need to call again the function in a recursive fashion. To embody these rules in a procedure, we indulge in a little wishful thinking, as we did in designing the rational number implementation. If we had a means for representing algebraic expressions, we should be able to tell whether an expression is a sum, a product, a constant, or a variable. We should be able to extract the parts of an expression, and for a sum, for example, we want to be able to extract the addend, first term, and the augend, second term. I never heard this term before. We should also be able to construct expressions from parts. Let us assume that we already have procedures to implement the following selectors, constructors, and predicates. So we know if an entity is a variable, we know if two variables are the same variable, we know that if an expression is a sum, and we know a bunch of stuff. And using these and the primitive predicate number, which identifies numbers, we can express the differentiation rules as the following procedure. And as I said before, these are the base cases, as you can see. If the expression is a number, we have a constant and we return 0. If the expression is a variable and if that that and if that expression is let me understand, is okay, if that expression is precisely the variable we are differentiating with respect to, we return we return 1. We return 1, otherwise we return 0, because if we are not differentiating with respect to another variable, we return 0. And then we have sum and product that recursively call this derive here and derive here with different logic. So here the derived procedure incorporates the complete differentiation algorithm. Since it is expressed in terms of abstract data, it will work no matter how we choose to represent algebraic expressions, as long as we design a proper set of selectors and constructors. This is the issue we must address next. That is, how to represent algebraic expressions. We can imagine many ways to use a list structure to represent algebraic expressions. For example, we could use lists of symbols that mirror the usual algebraic notation, representing ax plus b as the list a times x plus b. However, one especially straightforward choice is to use the same parenthesized prefix notation that Lisp uses for combinations. That is, to represent ax plus b as with the syntax notation, then our data representation for the differentiation problem is as follows. The variables are symbols. They are identified by the primitive predicate symbol. Okay, so we define the variable x. Okay. Two variables are the same if the symbols representing them are ic. Okay, so I guess this symbol is keyword of Lisp. Sums and products are constructed as lists. Okay, a sum is a list whose first element is the symbol plus. The addend is the second item of the sum list. And I guess the augend, I don't know if the pronunciation here is correct for this term, but if the second term of the sum is the third item of the sum list. A product is a list whose first item is the symbol star, and the reasoning is the same as in the sum procedure. Sorry, sum representation, where we have, instead of the addend and the augend, we have the multiplier and the multiplicand. Thus, we need only combine this with the algorithm as embodied by derive in order to have a working symbolic differentiation program. Let us look at some examples of its behavior. My God, this is terrible. The program produces answers that are correct. However, they are unsimplified. It is true that the derivative of x times y with respect to x is equal to y. But we would like the program to know that x times 0 is equal to 0 and 1 times y is y, and that 0 plus y is y. The answer for the second example should have been simply y. As the third example shows, this becomes a serious issue when the expressions are complex. Our difficulty is much like the one we encountered with the rational number implementation. We haven't reduced answers to simplest form. To accomplish the rational number reduction, we needed to change only the constructors and the selectors of the implementation. We can adopt a similar strategy here. We won't change derive at all. Instead, we will change makesum so that if both summands are numbers, makesum will add them and return their sum. Also, if one of the summands is 0, then makesum will return the other summand. Okay? This uses the procedure number, which checks whether an expression is equal to a given number. Similarly, we will change make product to build in the rules that 0 times anything is 0 and 1 times anything is the thing itself. Okay? Here is how this version works on our 3 examples. Much more readable. Although this is quite an improvement, the third example shows that there is still a long way to go before we get a program that puts expressions into a form that we might agree is the simplest. The problem of algebraic simplification is complex because, among other reasons, a form that may be the simplest for one purpose may not be for another. Okay, couple of exercises. And section 2.3.3, representing sets. In the previous examples, we built representations for two kinds of compound data objects, rational numbers and algebraic expressions. In one of these examples, we had the choice of simplifying, reducing, the expressions at either construction time or selection time. But other than that, the choice of representation for these structures in terms of lists was straightforward. When we turn to the representation of sets, the choice of a representation is not so obvious. Indeed, there are a number of possible representations as they differ significantly from one another in several ways. Informally, a set is simply a collection of distinct objects. To give a more precise definition, we can employ the method of data abstraction. That is, we define set by specifying the operations that are to be used on sets. These are union set, intersection set, element of set, and adjoint set. Element of set is a predicate that determines whether a given element is a member of a set. Adjoint set takes an object and adds a set as arguments and returns a set that contains the elements of the original set and also the adjoint element. Union set computes the union of two sets, which is the set containing each element that appears in either argument. Intersection set computes the intersection of two sets, which is the set containing only elements that appear in both arguments. From the viewpoint of data abstraction, we are free to design any representation that implements these operations in a way consistent with the interpretations given above. One way to represent a set is as a list of its elements in which no element appears more than once. The empty set is represented by the empty list. In this representation, element of set is similar to the procedure memq of the previous section. It uses equal instead of ic, so that the set elements need not to be symbols. Using these, we can write adjoint set. If the object to be adjoined is already in the set, we just return the set. Otherwise, we use const to add the object to the list that represents the set. For intersection set, we can use a recursive strategy. If we know how to form the intersection of set 2 and the coulter of set 1, we only need to decide whether to include the car of set 1 in this. But this depends on whether car set 1 is also in set 2. And here is the resulting procedure. Okay. In designing a representation, one of the issues we should be concerned with is efficiency. Consider the number of steps required by our set operations. Since they all use element of set, the speed of this operation has a major impact on the efficiency of the set implementation as a whole. Now, in order to check whether an object is a member of a set, element of a set may have to scan the entire set. In the worst case, the object turns out not to be in the set. Hence, if the set has n elements, element of set might take up to n steps. Thus, the number of steps required grows as omega n, theta n, sorry. The number of steps required by a joint set which uses this operation also grows as theta n. For intersection set, which does an element of set check for each element of set 1, and the number of steps required grows as the product of the sizes of the sets involved, or theta n squared for two sets of size n. The same will be true of union set. Okay, couple of exercises. One way to speed up our set operations is to change the representation so that the set elements are listed in increasing order. To do this, we need some way to compare two objects so that we can say which is bigger. For example, we could compare symbols lexicographically, or we could agree on some method for assigning a unique number to an object, and then compare the elements by comparing the corresponding numbers. To keep our discussion simple, we will consider only the case where the set elements are numbers. so that we can compare elements using greater or smaller. We will represent a set of numbers by listing its elements in increasing order. Whereas our first representation above allowed us to represent the set 1, 3, 6, 10 by listing the elements in any order, our new representation allows only the list 1, 3, 6, 10. One advantage of ordering shows up in element of set. In checking for the presence of an item, we no longer have to scan the entire set. If we reach a set that is larger than the item you are looking for, then we know that the item is not in the set. Okay? How many steps does this save? In the worst case, the item we are looking for may be the largest one in the set, so the number of steps is the same as for the unordered representation. On the other hand, if we search for items of many different sizes, we can expect that sometimes we will be able to stop searching at a point near the beginning of the list, and that other times we will still need to examine most of the list. On the average, we should expect to have to examine about half of the items in the set. Thus, the average number of steps required will be about n divided by 2, and this is still theta n growth, but it does save us on the average a factor of 2 in number of steps over the previous implementation. We obtain a more impressive speedup with intersection set. In the unordered representation, this operation required theta n squared steps, because we performed the complete scan of set 2 for each element of set 1. But with the ordered representation, we can use a more clever method. Begin by comparing the initial elements x1 and x2 of the two sets. If x equals x2, if x1 equals x2, then that gives an element of the intersection, and the rest of the intersection is the intersection of the cuders of the two sets. Suppose, however, that x1 is less than x2. Since x2 is the smallest element in set 2, we can immediately conclude that x1 cannot appear anywhere in set 2 and hence is not in the intersection. Hence, the intersection is equal to the intersection of set 2 with the cuder of set 1. Similarly, if x2 is less than x1, then the intersection is given by the intersection of set 1 and the cuder of set 2. Here is the procedure. Okay, understood. To estimate the number of steps required by this process, observe that at each step we reduce the intersection problem to computing intersection of smaller sets, removing the first element from set 1 or set 2 or both. Thus, the number of steps required is at most the sum of the sizes of set 1 and set 2 rather than the product of the sizes as with the unordered representation. And this is theta n growth rather than theta n square, a considerable speed up even for sets of moderate size. Cool. Couple of exercises. Sets as binary trees. We can do better than the order, and here I expect logarithmic growth. We can do better than the ordered list representation by arranging the set elements in the form of a tree. Each node of the tree holds one element of the set, called the entry at that node, and a link to each of two other, possibly empty nodes. The left link points to the elements smaller than the one at the node, and the right link to the elements greater than the one at the node. Figure 2.16 shows some trees that represent the set 1, 3, 5, 7, 9, 11. The same set may be represented by a tree in a number of different ways. The only thing we require for a valid representation is that all elements in the left subtree be smaller than the node entry and that all elements in the right subtree be larger. The advantage of the tree representation is this. Suppose we want to check whether a number x is contained in a set. We begin by comparing x with the entry in the top node. If x is less than this, we know that we need only search the left subtree. If x is greater, we need only search the right subtree. Now, if the tree is balanced, each of these subtrees will be about half the size of the original. Thus, in one step, we have reduced the problem of searching a tree of size n to searching a tree of size half n. Since the size of the tree is halved at each step, we should expect that the number of steps needed to search a tree of size n grows as theta log n. For large sets, this will be a significant speed up over the previous representations. We can represent trees by using lists. Each node will be a list of 3 items. The entry at the node, the left subtree and the right subtree. A left or a right subtree of the empty list will indicate that there is no subtree connected there. We can describe this representation by the following procedures. Mm-hmm. Okay. Okay. Adjoining an item to a set is implemented similarly and also requires logarithmic steps. To adjoin an item x, we compare x with the node entry to determine whether x should be added to the right or to the left branch. Okay, adjoining an item requires logarithmic steps. Yes, but then you have to rebalance at some time, I think. To adjoin an item x, we compare x with the node entry to determine whether x should be added to the right or to the left branch. And having adjoined x to the appropriate branch, we piece this newly constructed branch together with the original entry and the other branch. If x is equal to the entry, we just return the node. If we are asked to adjoin x to an empty tree, we generate a tree that has x as the entry and empty right and left branches. And here is the procedure. The above claim that searching the tree can be performed in a logarithmic number of steps rests on the assumption that the tree is balanced. That is, that the left and the right subtree of every tree have approximately the same number of elements, so that each subtree contains about half the elements of its parent. But how can we be certain that the trees we construct will be balanced? Even if we start with a balanced tree, adding elements with the adjoint set may produce an imbalanced result. Yes, indeed. Since the position of a newly adjoined element depends on how the element compares with the items already in the set, we can expect that if we add elements randomly, the tree will tend to be balanced on the average. But this is not a guarantee. For example, if we start with an empty set and adjoin the numbers 1 through 7 in sequence, we end up with the highly unbalanced tree shown in figure 2.17. Let's see. Okay, yes, this is highly unbalanced. In this tree, all the left subtrees are empty, so it has no advantage over a simple ordered list. One way to solve this problem is to define an operation that transforms an arbitrary tree into a balanced tree with the same elements. Then we can perform this transformation after every few adjoint set operations to keep our set in balance. There are also other ways to solve this problem, most of which involve designing new data structures for which searching and insertion both can be done in logarithmic steps. And more exercises. Lot of exercises. Sets and information retrieval. Let's see. example, example. Wow. Wow. Okay, I think I will stop right before this example. We have examined options for using lists to represent sets and have seen how the choice of representation for a data object can have a large impact on the performance of the programs that use the data. Another reason for concentrating on sets is that the techniques discussed here appear again and again in applications involving information retrieval. Consider a database containing a large number of individual records, such as the personnel files for a company or the transactions in an accounting system. A typical data management system spends a large amount of time accessing or modifying the data in the records and therefore requires an efficient method for accessing records. This is done by identifying a part of each record to serve as an identifying key. A key can be anything that uniquely identifies the record. For a personal file, it might be an employee's ID number. For an accounting system, it might be a transaction number. Whatever the key is, when we define the record as a data structure, we should include a key selector procedure that retrieves the key associated with a given record. Now we represent the database as a set of records. To locate the record with a given key, we use a procedure lookup, which takes as arguments a key in the database and which returns the record that has that key, or false if there is no such record. Lookup is implemented on almost the same way as element of set. For example, if the set of records is implemented as an unordered list, we could use blah blah blah. Of course, there are better ways to represent large sets than as an ordered list. Information retrieval systems in which records have to be randomly accessed are typically implemented by a tree-based method, such as the binary tree representation discussed previously. In designing such a system, the methodology of data abstraction can be a great help. The designer can create an initial implementation using a simple, straightforward representation such as an ordered list. These will be unsuitable for the eventual system, but it can be useful in providing a quick and dirty database with which to test the rest of the system. Later on, the data representation can be modified to be more sophisticated. If the database is accessed in terms of abstract selectors and constructors, this change in representation will not require any changes to the rest of the system. And we are done. And in the next video, we'll restart from section 2.3.4, the Huffman encoding trees. So, see you in the next video. Ciao, ciao.